video lecture, we are going to discuss the fundamental mode of vibration, stretching and bending modes of vibrations of H2O and CO2 molecules. We know that IR spectroscopy is the vibrational spectroscopy. That is, if something vibrates, it is going to be visible in the IR spectrum. All bonds in the molecule vibrate with a certain frequency. There are different types of vibrations. Some vibrations are visible, which are known as IR active, and some are invisible, and they are known as IR active. Stretching and bending are the two main types of fundamental vibrations in molecules. When there is a continuous change in the interatomic distance along the axis of the bond between two atoms, this process is known as a stretching vibration. Whereas a change in the angle occurring between two bonds is known as a bending vibration. Stretching vibrations require more energy than bending vibrations because they occur at high wave numbers. Each vibrational motion of a molecule occurs at a specific frequency, which is the characteristics of the molecule and the bond. There are two kinds of fundamental vibrations while studying infrared spectroscopy, that is, stretching vibrations and bending vibrations. We are going to discuss the stretching vibrations now. A stretching vibration is a movement along the bond axis such that the interatomic distance is increasing or decreasing. It occurs at high energies, 4000 to 1250 centimeter power minus 1. Two types in stretching vibrations. One is symmetrical stretching, another one is asymmetrical stretching. Bending vibrations. A bending vibration has a change in the bond angle. It occurs at lower energies, 1400 to 667 centimeter power minus 1. There are two types of bending vibrations. In plane bending, again we have two types, scissoring and rocking. Scissoring bending is atoms approach each other. Rocking bending vibration is atoms move in the same direction. Out of plane bending, wagging, that is, wagging bending vibration is atoms move up and down. Twisting bending vibration is atoms move above and below plane. It is a picture of molecular vibration. It has been divided into stretching and bending. And this is about IR vibrational modes. Stretching is nothing but back and forth movement, which involves change in bond angle, and which has got two types, symmetrical and asymmetrical. Whereas bending vibration is nothing but which involves change in bond angles, which has four types, scissoring, rocking, twisting, and wagging. Scissoring and rocking, they belong to in-plane vibration, whereas twisting and wagging, they belong to out-of-plane vibration. And this is a pictorial representation of those types. So, as we discussed, this is about stretching. For example, stretching is nothing but two bonds stretch like this. So, we have the elongated bonds. They stretch and they compress and they stretch like this. Asymmetric stretch is one bond will stretch in this direction, another bond will stretch in the opposite direction. So, like this. So, however, there is a change in internuclear distance, bond distance. So, what we call this as stretching. That is, movement of the atoms take place in the same direction with respect to the central atom. Whereas in bending, we have the type like scissoring. Scissoring means exact like a scissor. So, cutting of a scissor, so we know already. So, atoms approach each other, the bond angles decrease. So, this is scissoring like this. Now, the wagging is nothing but two atoms move to one side of the plane, they move up and down of the plane. Rocking is in plane. So in plane vibration. Okay. So twisting is one atom moves above the plane and another atom moves below the plane. So rocking is nothing but the movement of atoms take place in the same direction with respect to the central atom. Okay. So stretching, we have two types like this, and bending is, the definitions are given exactly in the square column. Fundamental modes of vibration. Types of molecule containing total n number of atoms. So for the linear molecule, the formula goes, the vibrational degrees of freedom, the formula goes like this, 3n minus 5. For a non-linear molecule, the formula to find out the vibrational degrees of freedom is nothing but 3n minus 6. So here, n is the number of atoms. 3n is nothing but degrees of freedom. So for example, here, translation degree of freedom is nothing but 3. Rotational degrees of freedom is nothing but 2 for linear molecule. So the formula goes 3n minus 5. Similarly, translation degrees of freedom for non-linear molecule is nothing but 3. Rotational degrees of freedom is nothing but 3. So we have 3n minus 6. Now, these are all some molecules. We are going to have the fundamental modes of vibration of those molecules, like for example NO, CO2, H2O, NH3 and so on. And we are going to discuss only two molecules, CO2 and H2O. One is a linear molecule, another one is a non-linear molecule. For example, when you take NO, the total number of atoms is nothing but 2. It is a linear molecule. The formula is 3n minus 5. You substitute n equal to 2 here. We will have 6 minus 5, which is nothing but 1. So fundamental mode of vibration is nothing but 1. And for CO2, we are going to use the same formula, 3n minus 5, because it's a linear molecule. So 3 3s are 9, 9 minus 5, that will give us 4. So 4 mode of vibrations are there. And just take H2O, it's a non-linear molecule, and use 3n minus 6 formula. Substitute n equals 3, and we will have 3 fundamental modes of vibration. So one can calculate for other molecules using this table. So vibrational modes in molecules. Number of vibrational modes are, we'll have to use for linear molecules, we'll have to use this formula, 3n minus 5 normal modes, and for non-linear molecules, 3n minus 6 normal modes, where n represents the number of atoms in the molecule. And this video lecture, we are going to discuss one linear molecule and another one is non-linear molecule. So water molecule and carbon dioxide. So we are going to discuss first water molecule, which is a non-linear triatomic molecule. 3 normal modes of vibrations exist: symmetric stretching, asymmetric stretching, and symmetric bending. Whereas in carbon dioxide, we have linear molecule, 4 fundamental modes of vibration. It includes symmetric, asymmetric stretching, and 2 bending modes. We are going to discuss. First, let us discuss the fundamental modes of vibrations of H2O. Let us learn the normal vibrations of water molecule. Here it is a water molecule and it is a non-linear triatomic molecule. This triatomic molecule consists of 3 atoms, so n equals 3. Here, 2 hydrogen atoms are bonded to an oxygen atom. Its structure is bent within HOH angle, which is nothing but 104.5 degree. Its degree of freedom is nothing but 3n. The vibrational degree of freedom for non-linear molecule is nothing but 3n minus 6. Therefore, this water molecule has 3 normal modes of vibration. So we have calculated using this formula, 3n minus 6. So we have 3 modes of vibration. So they are symmetric stretching, bending, and asymmetric stretching vibrations. And this is the structure of water molecule. The modes of vibrations of water molecule are represented as below. And so this is a symmetrical stretching. So symmetrical stretching, the hydrogen atom with respect to the oxygen, it moves exactly back and forth like this. So this is called a symmetrical stretching. So they change in dipole moment. So there is a change in dipole moment. So surely it must be IR active. And for the asymmetrical stretching, one hydrogen atom will go inside, the another will come out like this. See, like this. So this is called asymmetrical stretching. Again, there is a change in dipole moment because there is change in bond length. So surely there will be change in dipole moment. So this is also IR active. And another one is bending vibration. So there is a bending vibration. So surely there will be change in dipole moment. So this is also an IR active. So H2 molecule is a polar molecule having certain dipole moment. Its dipole moment changes in each vibration modes. So all fundamental mode of vibrations are IR active in H2O molecule. See here there are normal modes of non-linear triatomic water molecule are given here. So nu1 stands for symmetric stretching and which goes with the wave number 3652 centimeter power minus 1. So this is IR active. And nu2 is nothing but asymmetric stretching, which is higher than that of symmetric stretching. So look at the wave number. It is 3756 centimeter power minus 1. Again, this is IR active. Whereas symmetric bending, this is referred as labeled as nu3, which falls on 1597 per centimeter. And this is also IR active. Here the atoms move in phase with a simple harmonic motion in each normal mode. This water molecule experiences oscillating dipole moment due to non-linear behavior. So water molecule is infrared active. First we see symmetric stretching vibration. This mode of vibration is labeled as V1. Here the atoms move in phase and there are same displacement of two OH bonds. Both the bonds increase or decrease in length simultaneously. It occurs at a frequency number 3657 per centimeter. This mode is infrared active and an absorption band is observed at 3657 per centimeter in the infrared spectra of water molecule. The next one is asymmetric stretching vibration. This mode of vibration is labeled as nu2. Here there is stretching at one end and compression at the other end. One bond length is increased and the other bond length is decreased. It occurs at high frequency than the symmetrical stretching vibrations. This produces change of dipole moment and hence the molecule is infrared active and an absorption band is observed at 3756 per centimeter in the infrared spectra of water molecule. Here the arrow marks represent the relative atomic displacements. Then this is symmetric bending vibration. This mode of vibration is labeled as nu3. This mode corresponds to a bending of the molecule about HOH bond angle. This bending vibration is known as scissoring vibration. The bending motion produces change in dipole moment, so it is infrared active. And an absorption band is observed at 1597 per centimeter in the infrared spectra of water molecule. So here is the spectrum of infrared spectrum of water molecule. So there are three absorption bands here, and this is the first one, the highest one, which is nothing but asymmetrical stretch, which falls on 3756 centimeter power minus 1, and this is about symmetric stretching. The absorption band is, and second highest one, 3657 per centimeter, and the lowest one is nothing but bending vibration, scissoring bending, 1597 per centimeter. See here, and one for bending, and this is for symmetrical, and this is the highest one for asymmetrical. And the y-axis is nothing but transmission, and x-axis is nothing but wave number. And here also the same picture has been drawn here. The highest band is observed for symmetrical stretching, and the second highest is symmetrical bending, and the lowest is nothing but symmetrical bending. And this is symmetric stretching, 3657 per centimeter. The figure is the spectra of H2O molecule, which has three peaks. One peak is absorbed at 3756 per centimeter, and this corresponds to asymmetric stretching. The other band is absorbed at 3657 per centimeter, and it corresponds to symmetric stretching, the second highest. Then the other peak is absorbed at 1597 per centimeter, and this corresponds to symmetric bending. Here the bending absorption happens at a lower wave number than the two stretching modes because it takes less energy to bend the bond than to stretch. Here all the modes are infrared active and the three absorption bands are absorbed in the water molecule. Fundamental modes of vibration of CO2. Let us discuss now CO2 molecule. Now let us discuss the normal mode vibrations of carbon dioxide molecules. Molecules of more atoms are vibrate in more complex models. One molecule can vibrate in different ways. Each one of these various motions is known as normal vibration mode. Here it is carbon dioxide molecule. It's a linear triatomic molecule, so n equals 3. This molecule has 3n degrees of freedom. The vibrational degree of freedom for linear molecule is nothing but 3n minus pi. Use this formula 3n minus pi to calculate the number of mode of vibrations, which is nothing but 9 minus pi, which is equal to 4. So therefore, this carbon dioxide molecule has 4 normal modes of vibrations. Structure of CO2 molecule. The modes of vibrations of CO2 molecule are represented as below. The structure of CO2 molecule is nothing but linear molecule. The carbon dioxide is a linear molecule. And just now we studied about the modes of vibration using this formula 3n minus 5, which is nothing but 4. So out of 4 fundamental mode of vibration, the molecule containing n number of total atoms has n minus 1 number of stretching vibration. So which is nothing but 2. So 2 vibrations are stretching vibration and the remaining 2 will be bending vibration. Out of 2 stretching vibration, one is symmetrical stretching vibration and another one is asymmetrical stretching vibration. So this is about symmetrical stretching. So the first one goes with the symmetrical stretching. So the oxygen molecule, they stretch simultaneously and they compress simultaneously. Okay, see, since when they stretch like this and they were compressed like this, there will be no change in dipole moment because there will be no change in equal change in bond length. So there will be no change in dipole moment. So this is IR inactive. What is the next one? Asymmetrical stretching. And one goes like this, another one goes like this. So asymmetric stretching. See, we have asymmetric stretching. One is like this, another one is like this. See, so this is your asymmetrical stretching. And surely there will be change in dipole moment, and it is IR active. And for bending, we have 2 types. One is in plane bending, another one is out of plane bending. See here, this is in plane bending, and another one is out of plane bending. So this is one variety, and this is another type, out of bending. So in both the cases, we have change in dipole moment, and this must be IR active. And what is the energy? In both the cases, we have the same energy. What we call this is degenerate energy. So the remaining 3 vibrations are IR active because they produce change in dipole moment of CO2 molecule. The 2 bending vibrations have same energy because they are degenerate, doubly degenerate. So IR spectrum of CO2 molecule shows 2 absorption bands. The vibrations are labeled as usual, nu1, nu2 and nu3. By convention, it is a practice to label vibrations in decreasing frequency within their symmetry type. Thus, the symmetric vibrations are labeled as nu1, the highest frequency, and the next highest frequency is the asymmetric one, which is termed here as nu3. The nu2 vibration actually consists of two vibrations. One is in the plane of the paper, then another one is perpendicular, plane out of, so plane perpendicular to it. Hence it is doubly degenerate. They have the same energy. Thus they are symmetric stretching, nu1, two symmetric bending or scissoring, what we call it as nu2a and nu2b, and asymmetric stretching vibration labeled as nu3. First we shall discuss symmetric stretching. This symmetric stretching is enabled as nu1. Here the arrow represents the relative atomic displacements. Here it is a partial charge separation due to the oxygen atom at the end. So the magnetic moments are cancelled and the molecule becomes nonpolar, and no dipole moment is developed during the vibration. So the molecule is infrared inactive, and this mode occurs at the wave number 1300 per centimeter. Then here it is a symmetric bending vibration. This mode of vibration is labeled as nu2. This is symmetric bending vibration. So actually the nu2 vibration consists of two vibrations. One is in plane, another one is out of plane. So this is referred as nu2a and nu2b. So in and out of the plane of the paper. So these two bending modes of vibration have the same energy and differ direction of bending motion. Here it is doubly degenerate. Because of this, carbon dioxide molecule has one more mode of vibration when it is compared to water molecule. So these two bending vibrations are same and produced at the same wave number 667 per centimeter in the IR spectra of carbon dioxide. So this is doubly degenerate and they have the same energy, same wave number 667 centimeter per minus 1. Then this is asymmetric stretching vibration. Here this mode of vibration is labeled as nu3. Here there is stretching at one end and compression at the other end. This produces change in dipole moment, and this mode fits in the changing electric fields of the external radiation, and hence the molecule is infrared active. And this mode shows an absorption band at 2350 per centimeter in IR spectra of carbon dioxide. The spectra of carbon dioxide molecule is as shown in the figure. It has two peaks, one at 2350 per centimeter. This corresponds to asymmetrical stretching, and the other peak is observed at 667 per centimeter. This corresponds to two bending vibrations, and they are produced at the same wave number. And here is the figure for the infrared vibration spectra. So transmission versus wave number. So as we discussed, the symmetrical stretching will be IR inactive, and asymmetrical stretching is shown here. So which occurs the absorption band as 2350 per centimeter. And we have bending vibrations which you have two bending, in plane and out of plane. Both will have same frequency number, same energy, degenerate. So it occurs at 667 per centimeter. So IR spectrum of CO2 molecule shows two absorption bands. So here it is, two absorption bands. One is at 2350 and another one is at 667 per centimeter. So this is about asymmetric stretching, and this is about symmetric bending, doubly degenerate. And this picture is nothing but spectra of CO2 molecule, transmission with wave number. The stretching vibrations generally require more energy than bending vibrations. So they occur at high frequencies and wave numbers. Then the molecules having more vibration modes are apt to interact with in the electromagnetic waves. The infrared radiation is absorbed and emitted by carbon dioxide molecules, and it is not by oxygen and nitrogen molecules. The ability of absorption of infrared waves makes carbon dioxide a greenhouse gas. So let us discuss now introduction to application of vibrational spectra. Infrared spectroscopy provides the information about the presence or absence of specific functional groups. IR spectroscopy can provide a molecular fingerprint. This is a provide. Okay, this is spelling mistake is there. Can provide a molecular fingerprint that can be used when comparing the samples. If two pure samples display the same IR spectrum, it can be argued that they are the same compound. IR does not provide the detailed information or proof of molecular formula or structure. It provides the information molecular fragments, specifically functional groups. Therefore, it is very limited in scope, and it must be used in conjunction with the other techniques to prove a more complete picture of the molecular structure. So here there is a spelling mistake is there, to prove. The functional groups in any organic molecule can be identified. The unknown compound can be identified. One can compare, here it is compared. Okay, one can compare the spectrum. Purity can be determined. The kinetics of reactions can be studied. The inter and the intranuclear hydrogen bonds can be distinguished. The bond length, bond angle, dipole moment, and the molecular structure can be elucidated from the structure. The force constant can be determined. IR spectrum of a chemical substance is a fingerprint of a molecule for its identification. Like a fingerprint, no two unique molecular structures produce the same infrared spectrum. This makes IR spectroscopy useful for several types of analysis. Vibrational spectroscopy provides the most definitive means of identifying the surface species generated upon molecular adsorption and the species generated by surface reactions. In principle, any technique that can be used to obtain vibrational data from solid state or gas phase samples, for example, IR and Raman, and so on. IR spectroscopy is extensively used in different areas for varying purposes. Some of them are the studies of inter and intramolecular interactions, distinguishing free and hindered internal rotation, chemical reaction kinetics, pollution studies, hydrogen bonding, surface chemistry, catalytic process, establishment of molecular symmetry, and so on. Summing up, the IR instrumentation has advanced to a level generally beyond most of the spectroscopy's ability to interpret. The current challenge facing them is that of proper experimental design, interpretation of spectra, and use of appropriate data processing. Other applications of infrared spectroscopy are as follows. The unknown contaminants in industry can be determined using FTIR. Cell walls of mutant and wild type plant varieties can be found using FTIR. It can be applied for biomedical studies of human hair to identify disease status. The order and taste components of food can be identified. Atmospheric pollutants from atmosphere itself can be determined. Old paintings can be examined. It is also used in forensic analysis in both criminal and civil cases. For example, in identifying polymer degradation. The blood alcohol content can be determined. There are some limitations of the infrared spectroscopy. By IR spectroscopy, it is not possible to know the molecular weight of a substance. It does not provide information about the relative positions of different functional groups on the molecule. From a single IR spectrum of an unknown substance, it is not possible to know whether it is a pure compound or a mixture of compounds.